Hello, in today's video, we are going to be revisiting exothermic and endothermic reactions, and we are going to be talking about potential energy diagrams. Potential energy diagrams chart the energy changes during the course of the reaction. But first off, as a review, in our exothermic reactions, energy or heat exits the system. Therefore, energy will be released and heat will show up on the product side of the equation. So if we take a look at this example here, we see that heat is on the product side of the equation. Now, a lot of times it will say like 50 kilojoules. So if it's on the product side, it's going to be an exothermic reaction. In an exothermic reaction, the potential energy of the reactants is greater than the potential energy of the products because heat is released. So the products ends lower than where the reactants started. And also, when we have an exothermic reaction, the surroundings feel warm because heat was released. So if we have a beaker of water and inside there we have an exothermic reaction happening, what is occurring is that exothermic reaction is releasing heat. So that's going to cause the temperature of the surrounding water to increase. All right, so that previous slide was hopefully a review. On this slide here, we are getting into the potential energy diagrams. So first off, we know that this is an exothermic reaction because we start with 400 kilojoules of heat and we end with 100 kilojoules of heat. Therefore, we must be releasing 30 kilojoules of heat. All right, there's some different data points on here that you're going to be asked about. So the potential energy of the reactants. Reactants is what we start with. So potential energy of the reactants would be right here, that first arrow. Therefore, that would have a value of 400 kilojoules. Potential energy of the products would be over here. Products are what we end with. So it's how much energy we're ending with. And for this particular reaction, that is 100 kilojoules. Activation energy is something new that we need to talk a little bit more about. Activation energy is the energy needed to activate the reaction, to start the reaction. It is the difference between where you start and the top of the hill. So the activation energy, again, is the difference between where the reaction starts, so 400, and the top of the hill, so that's going to be 200. Activation energy will have a huge impact on the rate of the reaction. The more the activation energy, the slower the reaction is going to go because it's going to take longer to build up that energy and get over that hill. Our last data point is heat of reaction. So that is the amount of heat that is absorbed, or in this case, since it's exothermic, that is released. So it's going to be the difference between the products and the reactants. So difference between the products and reactants. So that would be this arrow here, number 4. So products are 100, reactants are 400, so heat of reaction is negative 300. It is always going to be negative for an exothermic reaction because it's releasing heat. All right, in our endothermic reactions, energy goes in for endothermic. So the reaction will be absorbing heat from its surroundings, which then will cause our surroundings to feel cold. So if we have an endothermic reaction occurring in a water solution, As that reaction is happening, it has to absorb heat from its surroundings. So that would cause the surrounding water to feel colder because then that surrounding water would have less energy. When we take a look at our potential energy diagrams in a second, you'll notice that the potential energy of the reactants is less than the potential energy of the products. So our potential energy diagrams for endothermic will look something like this. Because it's endo, it's got to gain energy, so therefore it has to end at a higher level. And with our endothermic reactions, heat shows up prior to the arrow on the reactant side of the equation. So this diagram here shows us an endothermic reaction. We know that it's endothermic because we are starting at 200 and ending at about 350. Therefore, the reaction is gaining heat. Heat is going in, so it's endothermic. We have the same data points that we did previously. So potential energy of the reactants. Reactants is what we have at the start of the reaction. So the energy at the start is 200 kilojoules. So that would be right here. The potential energy of the products, we have products at the end of the reaction. We produce the products. So the energy that we have at the end is equal to, on this diagram, about 350 kilojoules. Activation energy is the difference between where it starts, where the reaction starts, and the very top of that hill there. It's the energy needed to get the reaction going. So in this diagram, we are starting at 200. The top of the hill is 450. So the activation energy is 250 kilojoules. And our last data point, heat of reaction, that's the amount of heat that the reaction is absorbing or releasing if it is an exothermic reaction. So that's going to be the difference between where the reaction starts and where the reaction ends. So the heat of the reaction, we started at 200, we ended at 350. So that's going to be positive 150 kilojoules. All right, so now we need to talk in a little bit more detail about activation energy. So on our potential energy diagrams, let's say we have an exothermic potential energy diagram. Activation energy is this amount here. It is the difference between the reactants and the top of the hill. So all reactions need activation energy, and they're the energy needed to break the bonds of the reactants, and that's what gets the reaction started. So if we have reactants with stronger bonds, the activation energy would be greater. The greater the activation energy is, the slower the reaction would proceed because it's going to take longer to build up that required energy to overcome that. So on our diagrams, again, it's the energy to get us up over that hill, meaning it's the difference between where we start, that would be the potential energy of the reactants, and the very top point of the diagram. All reactions need activation energy, and activation energy is going to be a large factor in determining the speed of the reaction. The greater the activation energy, generally speaking, the slower the reaction will proceed. All right, another point that was on our potential energy diagrams is the heat of the reaction. So again, if we have an exothermic reaction, the heat of the reaction is the difference between the products and the reactants. It tells us the amount of heat that is absorbed or released over the course of the reaction. If we are to actually calculate the delta H, it's the heat of the products minus the heat of the reactants. Or I just take the difference between the two. And then I remember that if my reaction is exothermic, my delta H is negative. If my reaction is endothermic, I am gaining energy. So then the delta H is positive. One other thing that we'll be looking at is our heat of reactions are given on reference table I. So grab reference tables and open them up to table I now. All right, so here is table I. It gives us a whole bunch of different reactions and then their corresponding delta H values. They also, even very nicely, tell us that negative indicates an exothermic reaction. So they help us remember that. So in this first example, we have to literally find that reaction there. So now what we need to do is we just need to scroll through those reactions and find carbon plus oxygen gas makes CO2. So it is right here. My value for that is negative 393.5. So since it is negative, that tells us that our reaction is exothermic, meaning it is releasing heat. Now, question number 2 asks about this exact same, pretty much this exact same reaction. The only difference is this is the reverse of the previous reaction. So since we are reversing the reaction, we would then flip the sign and it now would be positive 393.5 kilojoules. So since we reversed the reaction from how it was written on here, we have to reverse the sign. All right, and our last thing that we need to talk about today is a catalyst. So we might remember from bio that enzymes act as catalysts. They speed up a reaction. The way that they actually do that is they alter the reaction mechanism, providing the reaction with a different course to take, and that different course has a lower activation energy. So if we have a potential energy diagram, let's say that looks like this. This would be the activation energy. If we add a catalyst, we're still going to start at the same spot, but we are going to change the mechanism. And now our reaction follows a different course. It basically takes a shortcut, and the shortcut now has a lower activation energy. So therefore, the reaction can proceed at a faster rate. Think about if you're out jogging in town. If you take a route with a lower hill, you are going to finish it quicker. So we still start and end in the same spot, but we find a shortcut that has a lower activation energy. It does not change the starting point or the ending point, so it does not change the value of delta H, but it will change the speed of the reaction.